In this electromechanical system, we have an electric circuit with an input voltage that is going to control a DC motor that applies a torque to the mechanical side, which is our rotor. And what we're looking for is the relationship between the output of the angular position and an output of the angular velocity of our rotor to the input, the voltage going into that circuit, EA. So we're looking for here two transfer functions. So we want to find the angular position, which will be capital theta over EA, and we want the angular velocity, so I'll call that capital omega over EA. So we have these two subsystems that are interfacing at the motor, the electrical system and the mechanical system. So we're going to start by treating them kind of independently and then link them together by that interface they have, the DC motor. And we're going to make some assumptions about the DC motor so that we can solve this problem, that it's going to have a linear relationship, that we know what some of the interface constants are, but we'll get to that in a moment. So we need some diagrams. The order we do them in doesn't matter. Since the electrical system is on the left, I'll start with that as my first diagram here. All right, so we are going to have, I'll redraw this so it's a little bit clearer, some EA voltage source that is the input into the system. And it's going to go through that resistor RA and an inductor LA. And then we come to the motor where we're going to have a voltage drop, and we can treat the motor as another of these kind of voltage sources, but we're going across the other way because it's actually a load. So we have some load and there'll be a voltage across it we'll call EB. The electrical side doesn't care in particular that it's a motor or a DC motor, it just cares that it's some load that will have a voltage drop across it. And then we can connect that back to our start point. And we'll assume that our current IA is going to be clockwise through this. So that's our entire circuit for the electrical side of this. We have a voltage source EA, goes through a resistor, an inductor across a load, and then comes back. So just a single loop there. So we'll be able to get that equation as we go through. While I'm in the diagram stage, I need a free body diagram as well. So let's look at a second equation here, or a second diagram. This will be the mechanical side. So I am going to have here the motor, and that's going to be connected to our rotor, which is then has this damper on the end of it. So I want to establish a coordinate system here. I'm going to just call this the x direction so that I can say I have the angle around the positive x direction is what we're calling theta here. So x positive right, and theta is, using the right-hand rule, positive around the x-axis. So let's look at what are the forces, the torques that are acting on our rotor side, on the mechanical side. Well, there's going to be the torque that is going to be given to us from the motor. So I'll call that T. That can change in time. So it is T of time, but I'll just call it big T here. We want to remember it is a function of time. And what other moments are going to be acting on this? Well, we have that rotational damper at the end. The rotational damper will always oppose the velocity. So it will be B times theta dot. And notice that is drawn around the negative x-axis, or it's going to be in the opposite direction of theta. And in this case, there's no other torques or forces acting on the rotor. And then I have my inertia diagram, and I'll really just simplify this down. I'll just bundle it all together, but it's that same rotor. So I have the inertia, which is going to go with the direction of theta, and that will be J theta double dot. And that's my complete free body diagram, forces and moments on the left, and my inertia on the right. So I have the mechanical side in diagram 2, I have the electrical side in diagram 1. So now I can start to develop some equations to get to where I need to go, the transfer function, theta over EA, and omega over EA. So my equation step. My first equation, I'm just going to do a KVL, and that is going to be for my electrical circuit. Obviously, there's only one loop here, so I know it has to sum to 0 because that's the rule for Kirchhoff voltage law. So let's see what happens as I go through my circuit. So I'm going to start down here, and I'm going to go up to the upper left. So I'm going across EA with the current, so I'm going to add EA. This is done in the frequency domain, so it goes to capital EA. Right, I'm going to go across then a resistor, so I'm going with the current. There's a voltage drop, so minus RA IA. I'm then going across an inductor with the direction of current, so minus an LAS times IA. I then go across well, it turns out to be a load, but I'm going with the current, but from the positive terminal to the negative terminal. So that's minus EB. And then I return to my starting point, so I am done. And we have one equation. Let's start to look at what we have. Well, the input is here. EA, we're told, is the input into our system. We have outputs of the current, IA, and the voltage across that load, which is the motor, EB. Again, IA changes in time, thus it's a function also of frequency when we take its Laplace transform. EB is a function of time, so when we take its Laplace transform, it becomes capital EB. So all of these terms are functions of time and thus functions of frequency. The constants like RA, LA, those are not affected by time. We're assuming the resistance is constant, the inductance is constant, so those don't change in time. They're just constants. So looking at what we have so far, two outputs. We have one input. The desired output of theta and omega are not here, and we obviously need more equations in order to solve this. So let's go on. We got the only equation we can out of the first diagram, so now we can go to our second diagram, which is now a free body diagram. We're now in the mechanical realm. So here I can take the sum of moments around the x-axis, which is going to be also the positive theta direction. So let's look at the left-hand side. So around the x-axis, positive around the x-axis, I have the torque T, which will be a function of time, minus B theta dot. And that's actually all on the left-hand side. B theta dot opposes the positive direction around x, so it's negative. And on the right-hand side here, I have J theta double dot. Now this is in the time domain. I'm always starting my free body diagrams, equation of motion in the time domain, but I want everything in the frequency domain for solving this electromechanical system. So I do want to take this and now do a Laplace transform. And I'll call that 2A. So this is the torque T is a function of time. So it's going to go to, well, it's already capitalized, so fancy T will be torque in the frequency domain minus BS theta equals JS squared capital theta. I'm making an assumption here. It does not say it specifically in the instructions, but because we are using transfer functions, I'm making the assumption that everything begins at rest. So initially our position is 0, our velocity, angular position is 0, angular velocity is 0, and then it's all at rest. We turn on this voltage, and then we are seeing how the rotor is behaving. It does not explicitly say that, but we need to assume that because we're not given anything about the initial conditions. So that's why all the initial conditions are going to be 0. So theta of 0 is 0, theta dot of 0 is 0, and that's why 2a simplifies nicely like this. So looking at 2a, what are the outputs? Well, we've actually added the torque, T, fancy T, and capital theta, the angular position. B is a constant, so that's fine. J is a constant. So we actually have 4 outputs now from the equation of motion coming out of the free body diagram. So we need at least 2 more equations. And if we look at our list of outputs and input is EA, and our output is theta. That's the first transfer function that we want. Omega doesn't appear and won't appear because, well, omega is actually the time derivative of theta when we're in the time domain. So it will not directly appear in the equation of motion because that always goes to those base, in this case, position. We're going to have to do a differentiation to get to our velocity, but that's fine. We'll do that when we go through the math. So going through our count now, we need 2 more equations, at least. Well, we haven't used the fact that the motor appears in both of these systems, the electrical system and the mechanical system. So we are going to put our 2 motor equations in. So first, we can use that back EMF equation. The problem doesn't provide us with this information, but we'll make the assumption that there is this linear relationship between the voltage drop across the motor and its angular velocity. So where we start is that EB will be equal to KE, some constant that will be dependent on what the motor is that we're using, times theta dot. Right, so the voltage drop, we are going to say, has a linear relationship with the angular velocity of the motor. We're in the time domain to start. I want to take the Laplace transform. So EB equals KES capital theta. Right, so now I'm in the frequency domain, so it matches what we have in 1 and 2a. And if we look, we haven't added any new outputs. EB was already there and theta was already there, but we do have this constant KE that we are going to have to, we would have to know it, or we'll just leave it as a variable right now, but that would be specific to the DC motor that we're using. How does the voltage across it relate to its angular velocity? And we can also add the motor torque equation that's going to relate the torque in the motor linearly to the current going across the motor. So the torque we already called T is equal to some constant, K sub T, times the current across the motor. Well, that was IA. Again, going back up to the electrical diagram, IA is the current across the motor we called, or the load, which has the voltage drop EB, and then the mechanical side, it provides a torque. So 4, I also want to take a Laplace transform and get 4a is little t, or capital T goes to fancy T, KT is a constant, and then this becomes capital IA. And if I look at my list of outputs, fancy T was already there, IA was already there, so I still have a total of 4 outputs, and now I have 4 equations. So now I'm going to be able to solve them and get, well, at least I can get my transfer function for theta. Then I'll have to do just a tiny bit of, well, calculus, but really in the Laplace domain to get my angular velocity, omega. So we're ready to take these 4 equations and go into Mathematica and solve for 4 transfer functions, but really just the one we care about right now, theta over EA. Now I'll transcribe those 4 equations that are in the frequency domain. So I'll just call it KVL. This comes from, obviously, Kirchhoff voltage law, so 0. So that's 0 equals EA minus RAIA minus LASIA minus EB. And that was from our circuit diagram. Now we have our equation of motion coming from the free body diagram. I'll call that EOM. And that will be then T, fancy T, minus BS theta equals JS squared capital theta. I am using the notation that matches what I have written down, but as long as we know what our variables mean, that's fine. So I did put this fancy capital T, and I did put capital theta here. So 2 equations down, and let's look at the other equations we have. Well, we have 3a, that is coming from the voltage drop across the motor related to its angular velocity. So 3a I'm putting in next, I'll call it equation 3, or actually this is the back EMF, so I'll call it back EMF, so remember where it comes from. So that came out 3A. 3A is E, B is KE. That's a new parameter that we're going to need to know, times S times capital theta. And then we have the motor torque equation. And that is the equation 4A. So I need to transcribe that. That will be fancy T equals KT IA. And I run those, and those are now in my system. So everything here is in the Laplace frequency domain, so I will be able to get transfer functions out. So we want to solve this list. We have KVL, EOM, the back EMF equation, and the motor torque equation. For, let's look at our list of outputs here. We have IA, EB, fancy T, and capital theta. For equations for the 4 outputs that we can potentially find transfer functions for. And something went wrong. Oh, I put in not capital theta, that's why it didn't work. All right. Now when I run it, now it works okay. And let's shorten this list. All right, so we have potentially those 4 transfer functions. It eliminated our dependent variables from the right-hand side, and we are in pretty good shape here. So remember, the first transfer function we want is that theta over EA. So I can go down here to this 4th one, and that will be my transfer function. I'll just call it TF1. It's the first transfer function I'm interested in. TF1 is going to be theta over EA, so I effectively divide through both sides by EA, and I get this transfer function. And I will take, I'll say TF1 equals, this is where I want it to do the algebra for me. Collect the numerator set of TF1 S, and then the denominator. So I can get into my form, basically the form I want. All right, so this looks good. I have an S cubed on the bottom, an S squared term, and an S, and I have a constant on top. So this is my theta over EA. And it's in basically the form I want. I'll just have to rewrite it in descending powers of S rather than ascending. But I also want that second transfer function. Remember from going back up here, I want omega over EA. But omega is the time derivative of theta. Angular velocity is the time derivative of angular position. So what I can do, as I've done in previous examples, is I can take TF1, which is theta over EA, and if I multiply it through by S, well, S times theta is omega. So the numerator is going to then be omega. Now we see it didn't really do a great job just doing the S here because I have an S on top, but I actually have S on the bottom, S squared, S cubed. This would work, but I can actually simplify this a little bit. So let's see if it's able to do it with a simplify. All right, so it was, but it's not now. It's not in the nice form I want, so I will do this step again to get it into the nice form. But I did want to reduce it as much as possible. That's why I'm going through this extra step. So we could have done that by hand. It wasn't that hard to just multiply through by S, but I'm letting Mathematica do it. So we see what happened. Well, since I multiplied this by S, all of the powers decreased by 1 in the denominator. So the S cubed went to S squared to S, and then S to just 1, that constant. So these are my 2 transfer functions that I wanted. So I'm going to transcribe them into, by hand, the proper form that I want for my final result. Now I can transcribe my final transfer functions. So the first one out of Mathematica, that was my theta over EA, the angular position over the input voltage. The numerator is fine, but I have to reverse the order of the denominator. So JLA S cubed plus BLA plus JRA S squared plus KEKT plus a BRAS. So that's our first transfer function, angular position for our output to our input of the voltage in the electrical side. Notice the denominator, well, really the whole transfer function has parameters from the electrical side, the LA, the RA, the mechanical side, it has the J, it has the B, and from the motor equations, the KE and the KT. All of it appear in this one transfer function relating a mechanical output to an electrical input. And this all came from the original equations because it's a position which was an output that appeared and a voltage was an input that appeared. The second transfer function is that omega over EA, which we got from differentiating capital theta. So these are the same. Omega is, in the Laplace domain, S times theta. So I'll transcribe this. And the numerator, again, is fine, KT. And all that really happened was all of the powers went down by 1 in the denominator when I multiplied through by S. So I have an S squared now. I have BLA plus JRAS plus KEKT plus BRA is my constant. And that's the second transfer function that I wanted, my output of angular velocity, mechanical, to an input electrical of the voltage at EA. So those are the two transfer functions that I was asked to find. Now we can look at a review. How did we get to these transfer functions? We were given this electromechanical system, so an electric subsystem coupled to a mechanical subsystem through a DC motor that is going to need an electrical input to provide some output torque and output velocity. So start by making a diagram for the electrical side, which was just, in this example, a simple single loop circuit, and then a free body diagram for the mechanical side. It's rotational, so I need to worry about torques and all of the torques and forces that act on the rotor. And we see that we have an input torque on the mechanical side, and that is the motor that also appears in the electrical side as an electric load. But we'll address that coupling as we get into the equation step. For now, it's a load in the circuit, and it's going to be a torque input in the free body diagram. So using the electrical circuit, just that single loop, I could do a KVL equation starting at the bottom left and going all the way around until I returned, so that the net voltage was going to be 0. So I gained voltage going across my source, and then voltage drops across the resistor and the inductor and the load, which is the motor. In the free body diagram, I got one equation of motion in the time domain. I took its Laplace transform so that I was in the frequency domain. Here, because I want transfer functions, everything needs to be in the frequency domain. So that was my second equation. At this point, I had 4 outputs and 1 input, but only equations 1 and 2a. I did not yet use the fact that there is a DC motor in the system that couples the electrical side to the mechanical side. So equation 3, I use the back EMF for the motor equation. That is going to be that the voltage drop across the motor is proportional to the angular velocity. Took that from the time domain into the frequency domain. Then equation 4, the motor torque equation that relates the torque that the motor provides to the current across the motor. So that is going to be a linear relationship that we're assuming that uses this parameter from the motor, KT. Again, starting in the time domain, I took the Laplace transform to get to the frequency domain. And now I have everything in 3a, 4a, 2a, and 1 in the frequency domain. I have 4 equations, and I have 4 outputs. And also importantly, the desired output of theta and the desired input of EA are present. So I took these 4 equations and I got my desired transfer function, or one of them, theta over EA, by solving the 4 equations simultaneously to get this transfer function. Then as a last step, because I also wanted to know how the angular velocity related to the voltage input, I can take my first transfer function, multiply it by S, since s times theta in the frequency domain gives me omega, the angular velocity. And that gives me the two transfer functions I wanted for this example.